Hi, this is Nick Siefert, and this is a practice presentation for one of the lectures in my Energy Systems Modeling course at Carnegie Mellon. And the topic here is nuclear fusion and fission and fusion power plants. I'll be discussing a little bit about the underlying physics, and then we'll eventually start moving into some of the applications for power plants. So let's start off with the basics. When you're above a temperature of about 10 to the 12th kelvins, you can form something what's called quark-gluon plasma. I'm bringing this up mostly because I don't want to confuse it with a different type of plasma that we're talking about later, which is when electrons are ripped off of atoms. And this is something called a quark-gluon plasma. Quarks are no longer confined, and they're in a free floating quarks and gluons are floating around. Okay. The reason I bring it up is that we're going to be using the word plasma later, and I don't want to confuse it because sometimes this word gets used for two very, very, very different types of matter. Okay, but above about 10 to the 12th Kelvin, quarks are not confined, and they're just moving around, and they can move around as collectively, but they're not tied into groups, as what happens when you go below of a temperature of about 10 to the 12th Kelvin, which is on an energy scale is about 200 MeV, mega electron volts. Quarks then are confined into species, and the two most stable are protons and neutrons. And the proton is made out of two up quarks and one down quark, and the neutron is made out of one up quark and two down quarks. Free protons have a lifetime that's greater than the life of the universe that we know of. And free neutrons have a lifetime that's only on the order of about 880 seconds, about 14 and a half minutes. So you might be wondering, well, how the heck how am I made out of protons and neutrons if neutrons aren't stable? And the reason is that a free neutron is not stable, but a neutron within an atom interacting with other protons can be stable, and can be stable for as long as we can measure. And but some neutrons are unstable, and shown on the bottom right here is what would happen in what's called beta decay, which is in some atoms when there's too many neutrons, one of the neutrons will decay into a proton, and what we mean by that is one of the down quarks will turn into an up quark, and then simultaneously there's then a release of a electron and electron neutrino, and so that's beta decay. Okay. Next thing I want to point out here is just show you a little bit about, when we're talking about power plants, we're talking about trying to use what's available around us. And so what I wanted to show was the abundance of elements in the Earth's crust. And because this will be important for noting what elements we have available for either fusion or fission power plants. The first thing to note is that there is both on Earth, there's an abundance of hydrogen as well as helium. Hydrogen and helium could be formed in the Big Bang. Okay. But the main elements that we have in our crust are those that can be formed within stars. So elements atoms between helium and iron can be formed with stars, and that's why their abundance in the Earth is quite large. The reason that any given element is more abundant than others has to do with stability. Often even number ones are higher than their odd counterparts. That's part of the reason why oxygen and silicon have such high formations, is the fact that they're even. And the next thing I want to point out is, but once you get to iron, as we'll see in the next couple slides, you can't form any elements heavier than iron within stars under equilibrium conditions. under normal, continuous. But what you can do is you can have when a star explodes, i.e. a supernova explosion, you can have a non-equilibrium situation in which for a brief amount of time you get to really, really high temperatures needed, and high temperatures and densities, and then you can form a lot of these higher abundant elements. And these higher abundant elements, as we'll see, we can drive energy in turning them more like iron, and that's fission. And then simultaneously we can take elements less than iron, such as hydrogen or helium, and start making them turn into larger molecules such as iron, and that would be fusion. So I'll also go through some nuclear basics. Main thing to note, the terminology is N for the number of neutrons, Z for the number of protons, and A for the total number of nucleons. So nucleon here meaning sum of protons and neutrons. So you get this, the formulas like X being the letters for that element, or for that atom, and then A being the superscript, and Z being the subscript. So for example, you might have U-235, which would be uranium-235 with 92 protons. You could have carbon-14, 6 protons. And the main, one thing I do want to note is often this last one over here shown is 31T, right? That really, sometimes that'll show up as, because that's tritium, sometimes you could write that as 31H, or sometimes it's used as 31T. So that it's really a form of hydrogen that has 2 more neutrons than hydrogen does. You could often see 21D, and that would be for deuterium. But other than hydrogen, normally what you'll see is the actual element as it would show up on a periodic table. But I do want to point out, because hydrogen is used a lot, different forms of hydrogen are used in fusion. Sometimes you'll see the terminology changed a little bit. Okay, some other things I want to point out. Proton rest mass, you can see, is about 338 MeV. And the neutron rest mass is just ever so slightly higher than that. And one key thing to note here is that the neutron rest mass is greater than both the proton and electron neutrino rest mass. And that's why you can say that the neutron is a higher energy state and does eventually want to decay into the lower rest mass energy states. Okay, the next thing I want to talk about is, and this is the key thing for what differentiates fusion from fission. So when I'm plotting here from the website, the next couple of figures will be coming from the website below, is the binding energy per nucleon. So it's B per A. Binding energy per nucleon, or A is the number of nucleons. So that binding energy is the difference, right? It's the difference in the rest mass of the constituent parts. So in this case, there's going to be Z protons and Z electrons and N neutrons. Right? So it's the difference between the rest mass of the individual particles compared to the rest mass of the atom itself. And so what you can see here is B of A is a positive number. It means it kind of tells you how much lower of an energy state is the atom compared to its individual components. And so it's always going to be a positive number for any kind of definitely for any stable atom. And the other thing to point out is hydrogen has shown down here. Hydrogen has no rest mass, and then you would go to the next deuterium and tritium, each of which have a small binding energy. And then we have a very, very stable binding energy with helium. Relatively speaking, helium is this would be helium-4, is very stable. And then after that, you actually get to lower binding energy. And so part of the reason why only hydrogen and helium are formed during the Big Bang is that Big Bang is a very non-equilibrium. It's not a steady state. It happens once and it happens very quickly. And so you get a lot of the, you can get some deuterium forming, and you definitely get a lot of helium forming, leaving behind still a lot of just plain old hydrogen. But you don't get these higher species out here. So that's everything from carbon. You see, you don't get much lithium or carbon. Even though eventually when you get to oxygen, the binding energies out here are greater than helium. It just, in the Big Bang, you don't have the time to form these. These species can form, though, under steady state in stars when you have billions of years for the atoms to react. So in stars, you can turn hydrogen into helium, and helium into carbon, and helium into oxygen, and oxygen into silicon, and then work your way all the way up to iron. However, once you hit iron, you kind of run out. And so when you get to iron up here, you run out and you maximize your binding energy per nucleon. And at that point in time, once everything turns into an iron, you have no energy left. And ultimately, though, the star will collapse. And very briefly, as it collapses, you get some gravitational energy that can be used to heat up. But it's not a steady state process. So locally, you can get hot, you get to really high temperatures and densities, and you can form some of these higher species, but you end up decreasing the binding energy per nucleon, which means it's not a stable, long-term stable. It's only kind of very non-equilibrium in this short amount of time that you can hold this high density and temperature. But once these are formed, they're ejected quickly, and then will eventually collapse into planets, and then can be used by intelligent species on those planets to run nuclear fission power plants, because you can derive energy in turning these higher species, higher nucleon, like large A, turning them back into stuff that looks more like iron. And as we've said before, we could also, those same intelligent species, be turning hydrogen and even lithium into things like into helium. Okay, so I want to talk a little bit about where that shape of that curve comes from. So here, this is B. The equation is for B, the binding energy. So to get to the last slide, we were B over A. We just divide everything here by A. So what we see here is that there's a number of different terms. The first one would be volume. Okay, so this term just depends on the number of nucleons. Okay, so if volume were the only thing that mattered, then you just have a constant binding energy. Okay, but we know that can't be the case. There's got to be other terms. So the next thing to assume is that just like for water droplets, right, you want to minimize the amount of surface. You want to maximize the volume for a given surface. So there's going to be some kind of negative energy associated with the amount of surface. So in that case, that term would look like A to the 2/3. Right? The first one, volume, just depending on the number of nucleons that you can pack. Surface depends on A to the 2/3. Right? The other thing to note is that we know that there's going to be other negative terms. Right? The more protons there are, the more electromagnetic repulsion there will be. That's going to be another negative term. So that's going to look like the number of protons squared. It looks like a Z times Z minus 1. But it's also the large. If you notice, there's an a to the 1/3, which looks like a 1 over radius. Right? It's not just, it's z squared over r. And then there's going to be some other terms having to do with symmetry and or pairing, and these are normally pretty small. But when you combine them all, you can see we can go from the black to the red to the green and finally to the blue. And you can see that you get that maximum right around on the order of 50 nucleons, which is around iron. So I just want to point out this is why that shape of the curve can be predicted from fairly simple physics principles. Okay, next thing I want to point out is that there's going to be regions. There's a lot of different possible proton and neutron combinations you could put together. However, what we have found experimentally over the years is that there's kind of this line of stability that, at least initially, follows the line of number of protons equal to number of neutrons. But then as you get to higher and larger molecules, you start needing more neutrons compared to the protons. And you can eventually even get into the point where you almost have 2 times as many neutrons as you do protons. Okay, so black here is the line of stability, and then these other colors, like red, are for a decay of a positron, and here this is beta decay. Finally, way up at the top, we can get some alpha decay, which we're losing 2 protons and 2 neutrons, and then we have regions which are possibly stable, and then way out here would be not stable. Okay. So then that leads us to, if we're trying to actually produce power here, we can see what we want is to take one of those very, very large atoms and turn them more into iron-like atoms. And one way of doing that is to take uranium-235, and if it collides with a slow-moving neutron, there's a good chance, a large cross-section, for it to split into 2 daughter atoms. It can turn into a lot of different type of daughter atoms. Shown here are 2 examples. Way at the top would be barium-142 and krypton-91, but you can also get krypton-90, barium-144, and 2 neutrons. So there's a lot of different possibilities you can form. The average number of neutrons that are produced per reaction, a mother uranium turning into 2 different daughter products, is 2.4 neutrons per reaction. So you can see if this continues and continues and continues, you can very quickly get to what we call the criticality, in which the number of neutrons is growing exponentially. Okay, so those products have Z values between about 30 and 60, which means even those products can often still have capability of, they're still heavier than iron. So we're still not getting all the energy out that we could from this process, but we're getting a fair amount of energy, and that kinetic energy is in the form of the neutrons, and those neutrons can eventually be absorbed and turned into thermal energy, which can then be used, can be heat transferred to a working fluid in either a Rankine or some kind of Brayton cycle. So if it's transferred to water, we can have a Rankine cycle, or perhaps if it's transferred to helium, we could design some kind of closed Brayton cycle. So that leads us to the cycles, and there's going to be 2 main cycles that we want to talk about in this lecture, but in this slide we'll talk about all the different kind of possibilities that are being discussed right now. Okay, so in the first one, we'll call it a direct single coolant Rankine cycle, and this is sometimes called the boiling water reactor, BWR. And in this case, our working fluid is going to be actually also the coolant into the reactor core. So there's no separate heat transfer going on. The liquid that we're going to be using in our Rankine cycle is going to be directly entering the core of the nuclear reactor. In this case, we have water. It's going to be boiling inside the reactor, and then we're going to use that steam to run a steam turbine. Okay. Those were kind of, let's say, the early designs. Later designs are more of the pressurized water type. There's kind of, you can think of it as one working fluid, one coolant. Okay, so in this case, there will be pressurized water that will be in the core, and then there'll be heat exchanged to the working fluid, which is also often water. And there's two main different types called the light water or heavy water, and that just depends on the coolant inside the core. Can either be water H2O or what we call heavy water, which would be either HOD or D2O. D here meaning deuterium, and that's why it's called heavy. It's not that the water is actually that much heavier, as you know. It just, heavy is to describe the fact that it is deuterium rather than normal hydrogen. Okay, and then you could have other 3 coolant designs, or you could have direct coolant where you have sending helium gas into your reactor. So that's often called the high temperature gas reactor, but we're not going to talk about that one in this class, this lecture. Okay, the commercial reactors in the US are entirely boiling water reactors or pressurized water reactors. Okay, there's 2 things to note here, or a couple things to note here. The first is that 2 main types of uranium that are important. The first is 235. That's the isotope that's responsible for fission, and its natural occurrence in the environment is about 0.7 weight percent. So the other 99.3 weight percent is primarily 200 and U-238, which does not produce fission, but it can parasitically absorb neutrons. Okay. Another thing to note is the fast neutrons released within 235 reaction must be slowed by a moderator. So the 235 needs to absorb low energy neutrons. So there needs to be that's why there needs to be a moderating material. And other things to note is, as we said before, in most power plants they're using light water, so that's H2O, but there is also those higher form. There's also heavy water reactors, such as at CANDU, in which they're using deuterium oxide. Okay, and what's happening here is that the cross section for absorption of neutrons with hydrogen are greater for hydrogen than they are for deuterium. So what that means is that light water reactors are always parasitically absorbing neutrons, and part of that means that you need to increase the amount of 235 compared to 238. Right. So in a light water reactor, you often need about 3 to 5% weight 235 uranium. However, in heavy water reactors, you can get away with on the order of 1 weight percent, so only slightly higher than in natural uranium, which means that they also are less like. It means heavy water reactors are actually safer from a kind of a weapons, nuclear weapons proliferation standpoint, because you can get away with a lower percentage of 235 uranium. So very interesting, the CANDU reactor and other heavy water reactors are actually from a nuclear fission point of view, they're safer from a fission proliferation. You do, though, of course, have more formation of tritium in those reactors. So in the fusion sense, maybe they're not as safe, but because tritium can be used to make fusion bombs, as we'll see. Okay, so let's go out, let's talk a little bit. Here's a process flow diagram for the boiling water reactor, such as at the Fukushima Daiichi reactors. And so in this case, as I said before, the actual working fluid for the Rankine cycle goes into the core and boils. Okay. So the key things here is less number of less equipment. However, we now have to deal with boiling inside the core, and that can often be less safe than what we're going to be showing in the next slide, which is the pressurized water reactors. So in this case, in the core itself, you have high pressure water that doesn't boil. Okay. And that's going to be heat exchanged. So here in the core, you have one fluid. That's going to be heat exchanged with your working fluid, which would then go through the turbines to generate electricity. And then you have condenser and pumped back up before it goes into the system. Key thing here is that there's no boiling occurring in the core. But you can see we have a lot more equipment here, so it's more complex. And so, as I said before, CANDU is one of the examples of a heavy water reactor. And there's about 30 as of 2012. There were about 30 of these worldwide. And so the main thing here to note is that from a fission proliferation point of view, these are safer because you can get away with a lower amount of uranium-235. So you can operate under amounts of U-235 that could not be turned into fissile weapons. However, of course, that comes at an expense because now with all this deuterium can absorb neutrons and form tritium. And tritium, though, could be used in fusion weapons. However, I think the bigger concern is nuclear fission propagation than worrying about people trying to make fusion. It's very, very, very difficult to make a fusion weapon. So, but just trying to point out that there's always going to be trade-offs. Okay, so that does now lead us to where we were talking about tritium, right? We can have deuterium and tritium, and we can make a fusion reaction. So here, fusion is extremely exothermic. We take this is one of the many different type of fusion reactions, but the one most interesting probably for producing electricity on Earth, and that's when a deuterium and tritium combine, and they form helium and a neutron, and that energy is carried away by the helium and the neutron. Most of that energy is carried away by the neutron because of you can think of conservation of momentum, right? The neutron and the helium are going to have roughly the same amount of momentum, which means they're going to have an unequal amount of energy. Most of the energy will be in the neutron, about 80% in the neutron, 20% in the helium. Okay, another thing to point out is there's no change in the number of electrons, protons, or neutrons, right? So there's it's just a all we're doing is moving around the protons and neutrons. We're not it's not like in beta decay where you actually have a change in the number of neutrons and protons. This is not a weak reaction. This is purely mediated by the strong nuclear force. Okay, so when it comes to fusion, as I said before, in the last slide I showed you the deuterium-tritium reaction, but there's other type of fusion reactions you could have, such as DD, so two deuterium can combine and form a helium-3 and a neutron. So that's one option you have. and or you could have deuterium and a helium-3, and they can combine to form a helium-4 plus a proton. So helium-3 means that you have 2 protons and 1 neutron. So you can think of it as a not quite, it's a less stable form of helium. But it's got an extremely long lifetime, which is why you can find small amounts of helium-3, though mostly it's helium-4. So what's shown here is the reaction rate for fusion, basically related to the cross section, and this is temperature in billions of Kelvin on the bottom. Shown up here is temperature but in units of kilo-electron volts. So you can see there's a maximum, and then there's often the rates start decreasing, and but the rates for deuterium, tritium are much higher, like orders of magnitude higher than they are for DD or deuterium with helium-3. So that's part of the reason why fusion, if we have commercial fusion, it's likely going to be deuterium, tritium. And another way of showing that is if you plot on this case the number density of electrons times the time, tau. Here tau is time. It's the confinement time. So confinement time for fusion plasmas can be increased with higher magnetic fields or larger fusion reactors. So both of those two things can increase tau, and the number density can be increased with larger magnetic fields and or higher, basically with higher magnetic fields. So think of this axis here as the amount of magnetic field and size, and then over here you have temperature, which is also somewhat going to be related to the amount of magnetic field. And you really want to get to the lowest value of what we call N tau T, NT tau, and that's the Lawson criteria. And basically on this graph here, right, you can see this term goes inversely with temperature. So that means what we need to do is we need to get above, for fusion to occur, we need to be above this line. So we can either do it at really, really high densities and confinement and somewhat low temperature, or we can do it at higher temperatures but lower confinement time times density. But either way, we have to get above this, and this line here is the Lawson criterion. It says NT tau must be greater than 10 to the 21 keV times seconds divided by meter cubed. Okay, so you can see we can get above that, and that's the criteria for DT reaction. We would need the Lawson criteria for DD and DH. Values are much, much higher, which means it's much harder to get to. And so you can kind of think of it as DT is going to be the first step. It's the easy, it's not easy. As we'll see, it's very, very hard even to get here, but it's going to be the first stop on the way. I do want to talk a little bit about inertial confinement fusion, but mainly because this is one of those ones where it gets a lot of hype sometimes, and I just want to point out inertial confinement fusion is mainly a means for testing fusion weapons, but sometimes it gets sold as like an energy technology of the future. It could be, it's just they are really, really, really far away from ever getting to a break even. They're 3 orders of magnitude away from break even right now. Whereas on the plasma, the fusion plasma, they're getting very close to the point in time in which they're break even, and by some standards they're pretty much getting close to the amount of nuclear energy coming out of the reaction is equal to the amount of energy they're putting into it. Okay, so what I want to show here is this is that fusion triple product, and this is temperature here. And these are a number of different fusion reactors over the years. And generally speaking, these ones down here were from the 1960s, 70s. And some of the latest ones, like JET, which is in England, have gotten close to what we call QDT is equal to 1. Meaning the energy coming out of the reaction, total energy, neutron plus the helium formed, is equal to 1. And what we need definitely the amount of energy coming out from the helium to be greater than the amount of energy we put into it, right? So that's at least, we're talking about, we need at least Q is equal to 5 or so. We'd probably want to be ideally operating around Q is equal to 10, maybe. ITER, which I'll be talking about, ITER, which is being built right now in France, is going to be just below what would be needed for ignition reactions, meaning we still need to get a little bit better than ITER in a commercial device, and that would be kind of a follow-up reactor, which may hopefully be, there's no current construction of any larger facilities after ITER, but there's a lot in design right now. And so here's what ITER looks like. It is yet to be the vessel itself has yet to be put together. Right now, the building has been set up. A lot of the individual components have been made, but they haven't been all put together. But this is what the scale looks like. Here's a couple people down here. Right, this thing dwarfs the size of people. This is going to be extremely, extremely large, but it will get us pretty much to knowing whether or not we can kind of reasonably build fusion reactors. It's not going to be, it's not a commercial facility. It's for testing science, but it will get us really close to being able to understand whether or not fusion power plants are going to be possible. So just to talk a little bit about what the power plant would look like. You have the plasma inside here being confined by the magnetic fields. And as I said before, the byproducts are helium. Helium is used to heat up the plasma, and neutrons are formed. The neutrons are going to leave the reactor, the inside of the reactor, go through the wall, and hit what's called the lithium blanket, at which point in time the neutrons will collide into lithium, and they will make tritium and helium, and sometimes tritium, helium, and another neutron. Okay, so what this means is the net result is that when we said deuterium and tritium is not a stable, you don't just find tritium around it. It has a half-life and will decay into deuterium. But deuterium, there's deuterium in seawater, enough to run the economy for thousands, if not millions of years. And so really the net result when we're talking about nuclear fusion, we're talking about taking deuterium from seawater and lithium, which is also quite abundant, deuterium and lithium, and turning it into two heliums. So that's the net result, deuterium plus lithium going into 2 helium. And so that's the overall reaction. It's extremely exothermic to turn deuterium and lithium into deuterium and lithium into 2 helium. Extremely exothermic. There's no CO2 emissions, right? There's no NOx, SOx, no particulates, right? We have basically a clean energy source. A lot of energy then can go out to be heating steam to generate then electricity. So this is kind of the concept for fusion. We don't have concerns of radioactive. I should say we don't have. You can have some radioactivity going on because there are some neutrons, but they can be normally minimized, and it's just going to be within this reactor, and then you have a decommissioning to deal with that. But you're not producing plutonium or other materials that could be used in weapons. I should say nuclear fission weapons. So we have potentially extremely safe. The other thing to point out is nuclear fusion is not. There's no criticality going on. There's no chain reactions. If you turn off the magnetic fields, this thing will just stop running, right? There's no way for this to turn into an explosion. And so that's one nice thing about nuclear fusion is you cannot, have a nuclear explosion going on here, right? All you can have is that energy will dissipate into you turn off the magnetic fields, the energy is just going to dissipate into the walls. So I want to then end this lecture on what could be potentially, right now, as you can see, it doesn't look like it's very cheap, but potentially we have a extremely clean energy source for the future, in which we have no CO2 emissions, no NOx, SOx particulates, and so that's where I want to end off. It's the potential, but as they always say, it's 50 years off. Okay, that's all.